Hey, what's up, YouTube? So today I think we'll get a little bit into predicting error. At least the lesson plan goes into trying to log some error metrics, which on the Vibe Coder repo, the current optimal start block has some of those features built into it. This is actually running at a building in a VRF system. The conditions are kind of mild outside, so that's not a lot of not a big demand on it to run. But currently, at the moment, it's the building's unoccupied and it's only drifted about 4 degree, not even 4 degrees from set point. So this is the current set point. We're at 69 degrees, and then this is the last run. The last time this block ran, which there's not a lot of data, it took about 6 minutes for the zone to catch up to set point. And it actually, no, it predicted 5.96, and it actually took 6.42 is what the algorithm inside recorded, which had some error of about 30 seconds. I don't know if this is like a very good example to use. There's not a lot of data on it either because it hasn't been running for very long, but I think you get the basic idea. So yeah, this is the stuff we've been talking about. This is actually logging. It's running the quadratic model inside of it, but for just for a visualization for metrics to trend, it still calculate the linear degree per minute, which it is kind of running about 0.029 degrees per minute. And at the moment, inside these blocks, you can always go into, even though the schedule, even though it's not actually running right now, the model is always predicting. So it's predicting 6.16 minutes of runtime based on this temperature being off from set point. So it's kind of cool. Maybe we'll get into this a little bit more. But thought I'd show you guys a little bit about that. Please reach out if you're ever interested in setting this stuff up and have some questions. All right, so let's get into the last day of day 7, the linear model. The limits of linear. Goal is to understand when linear models break down, because they've been talking about the physics in heating and cooling buildings aren't exactly linear. It's kind of well known that it's not linear. So that's why the degree per minute models can kind of fall short. So linear models assume constant warm-up rate or cool-down rate, but buildings are complex. On very cold mornings or deep setbacks, heat transfer slows down and the zone approaches set point. Linear models also ignore external influences like outside air temperature or thermal mass. Use this review to reflect when model 0 is adequate and when you need to draw on more advanced models. Okay, how to use it. Apply the concept using the formula algorithm provided. Mini example for demonstration. Understand why this matters. I'm just kind of skipping over this. Here's a little example. These are like these list data structures. So this would be some previous runtime of 0.2 degrees per minute. And then this would be how far off you were from zone temperature and set point. Kind of like what I was showing you, the previous stored data and then actual previous runtimes. So then it's just calculating this, predicting, just the rate. We've been doing this all along. Okay, so for this is, for example above, compute the percentage of error. So this is what it's wanting us to do. Okay, so we could just try this once. Compute the percentage of error. Alright, so maybe I'll just take this and might actually just get out of this for the time being. Hold up, where'd the code go? Okay, so I'm just gonna recopy this, get back into VS Code. Let's just run this. Python math lesson. Alright, so with a 3-degree delta, we predicted 15 minutes and it actually took 16 minutes. And then with a 8-degree delta, we predicted 40 minutes, but it actually took 70 minutes. So kind of a big error in there. So I think like what we could do is just calculate just a percentage. So let me see. Where would we add here? To real world. Okay, so if we can compute the percentage of error here, so I don't think it's very much here, but we could just say error equals let's see, so I think we could just basically say actual minus predicted. So let's see, I'm just trying to look and see how they did this. Delta and the rate, so predicted, so I might just print actual. Actual is actually this right here. So we could just say error equals actual minus predicted. See what that comes out. Actually, they abbreviated it here. Predicted. I think we just have to divide it by 100. Well, here, let's just try something. Print error, and I think we could do error. Error is 0.3. Well, maybe we could actually try, let's try this, actual times 100. And like we could even do the round feature. So we could say, could even do another, add in another string, see what this looks like. Okay, so I think we satisfied this lesson here of computing the percentage of error. Just, so this run we were off by a minute, which was 6.25%, and then this run we were off by considerable amount, like 30 minutes, which I have ran into as well. So like there's times when these models predict really well, and there's times when these models don't predict very well at all. So yeah, 42% error. So I think that sums it up with the Model 0 tutorial for this week, and then next week we'll do more of the kind of the more advanced, getting into more advanced, the quadratic model. I also have in the repository, there's this sample Pi files. So this is just kind of sums up, basically you could run this and this would be pretty much like what we've been learning. So I might just do Python model 1 tutorial. Whoops, sorry, actually we're still on model 0. Here's a model 0. Alright, see what this prints. Alright, so like this is actually, we can walk through this script here, but it's actually printing delta temperatures. So this is, remember, the zone temperature before the building starts, and then the delta of the occupied zone set point. So it's either in this first day we're either 2 degrees above or below the occupied zone set point, and recorded time of 10 minutes. So today's update, so it's updating its exponential moving average. And yeah, this is basically stepping through the final learn rate. So this is 15 days worth of data. So this is kind of like what on the Vibe Coder repo, the linear model, which defaults to 15 days of data. So every time the model, every time we execute and rerun the script, it'll update. It'll get rid of the oldest data and capture newest data, and then we'll keep on continuously updating this linear model in degrees per minute. So this is exactly what would happen in Java code in the program object. And we could actually try and just walk through this real briefly. So it's basically using some statistics, a loop and a sum. I'm sorry, this is the wrong script. Model 0. So we're looking at the right print here, but it's the wrong script. Sorry about that. So this is the saved data. So we just have like a default 0.1 degree per minute, which the Java code does in the program object too. Like we always just have a starting point of 1 degree per minute, and then a starting point for the EMA weight, and then we basically we plow through this data and update this EMA every time. So we kind of step through all of that here, and then we end up calculating our final linear model right here. And then this is just made up. So it's predicting that tomorrow's delta t, which I'm not doing. We're just doing actual delta t's before the building starts. But they're just throwing in some, if it was a 10 degree delta based on this model here, we would take 50.1 minutes to warm up. So I guess that is something that you could do in theory. If you could theoretically predict what would be the delta t tomorrow, we would need 50.1 minutes of HVAC runtime. So I haven't even thought about that, but like predicting future HVAC runtimes based on a future delta, yeah, this is a little above and beyond, but kind of cool. I'll have to think about that a little bit more. So thanks for watching. Stay tuned for tomorrow on day 8. I think this stuff is kind of fun. It would be cool to turn this into, maybe by the end of this, we could actually have more of a production app. I think that'd be really cool to see what this looks like in the field in Python or Java. See you tomorrow.